Hi, my name is Trevor Reese. I'm a master's student in CIS 566, and my design pattern is the scheduled task. The intent of the scheduled task design pattern is for real-time systems. It ensures that the operations of these systems, which are usually processes, are performed at a certain frequency required by the system, and they finish within their timing constraints. They also provide a way so that higher priority tasks can interrupt lower priority tasks. This is also known as preemption.
The main background motivation for the scheduled task pattern is for use in real-time systems, which are computing systems where performance is measured by the system's ability to ensure that its tasks perform their functions and complete within certain time constraints. If you haven't taken ECE 554, it goes more in depth into this topic. There are three types of real-time systems, each of which places an increasing importance on adhering to deadlines. The first of these is a soft real-time system, where missing deadlines can be a nuisance, but not all value of the system is lost. Think of something like a web page or an arcade game. Firm real-time systems can recover from some missed deadlines, but continued failures can have significant negative effects. Something like bank software would fall under this category. Finally, hard real-time systems are ones in which missed deadlines can be dangerous or even deadly. Defense systems and radiation devices fall into this category. Real-time OSs are responsible for creating optimized task schedules, managing memory and I/O, and recovering from system crashes.
In addition to meeting system time constraints, we want a task structure that meshes well with a real-time OS, where the OS itself can call these tasks. We want to allow for preemption, so higher priority tasks can interrupt lower priority ones, and we want to be able to optimize our scheduling so every task can get scheduled properly. The class structure of this design pattern is fairly simple, as it only consists of two main components. The first of these is the scheduler, which is not to be confused with the scheduler pattern. The scheduler keeps track of tasks, fits them into its schedule, and executes them when they need to be run. The tasks keep track of how often they need to run and how long they take to run. The task class is actually an abstract class which can be apparent to any more specific concrete task. The scheduler shouldn't know anything about each task other than its time constraints and how to execute it. Some systems represent the scheduler as a task with very high priority or run it as an interrupt handler. Otherwise, it can just run in the background and allow certain amounts of time for executing tasks. Time in the system can be represented in any way, as long as it is consistent across tasks. This pattern provides a fairly loose structure, so the actual members and methods of each class are up to the programmer. The algorithm used by this pattern guarantees that the set of tasks it needs to run are schedulable. This means that the system can mathematically guarantee, even in the worst case, that all tasks can be run before their deadlines. To ensure this, it builds the schedule using the rate monotonic algorithm, which is a fixed priority algorithm in which the most frequent tasks are scheduled first. For this algorithm to work, the sum of each task's time cost over its time period must be less than or equal to the CPU utilization, which is given in the formula on the slide. The scheduler won't attempt to schedule tasks it knows it can't schedule. The algorithm builds a schedule frame, which is the smallest possible schedule that can repeat identically and indefinitely, while satisfying all time constraints. The size, in time units, is the least common multiple of the task's time periods. In the example below, the least common multiple is 20, so that is the size of the frame. Each task is then scheduled in order from smallest time period to largest, taking as much time as needed in the worst case to complete. Here are some consequences of using this design pattern. This method of scheduling tasks is reliable and efficient, while mathematically guaranteeing that each task will run and meet its deadlines. The scheduler can schedule tasks without any knowledge of their contents, as it doesn't need to know. While we discuss processes in real-time systems, this pattern can scale up to something like scheduling cloud computing jobs or other large batch processes. There are a few caveats to using this pattern, however. It requires that the time cost for tasks be known ahead of time and be deterministic between runs. It assigns fixed priorities to tasks so they cannot change at runtime, and it assumes that no task relies on another for data.
While implementing this pattern, here were the three main classes I used. You'll notice I said 3 instead of the 2 mentioned on the structure slide. This is because task is an abstract class, so I needed a simple derived class for a demonstration. The scheduler class keeps track of the tasks it needs to run, creates a schedule of how to run them, and provides public methods for adding tasks, clearing the schedule, and running the current tasks. The task class keeps track of its progress and how many times it is run for its time constraints, as well as the constraints themselves and a task ID. It provides a constructor, getters for its parameters, and a method to execute the task. The child class for task, simple task, has a blurb to say what it is doing and a virtual execute method so it can be called from a parent pointer. Here's the code used for rate monotonic scheduling. The block on the left is run whenever the caller attempts to add a task. It calculates the CPU utilization based on the formula I showed earlier and compares it with the potential load when another task is added. If the load is greater than the utilization, it does not add the task. The second block is for creating the schedule. It calculates the least common multiple of the task time periods and resizes the schedule frame to fit them. It loads the tasks into a priority queue and extracts them based on their time period. The scheduler then walks through the schedule frame and schedules tasks as it can in the earliest possible time slot. This is the code used for executing tasks. The block on the left is in the scheduler run tasks function. It walks through the schedule frame and determines the starting and ending timestamps for each execution segment. It then calls the task pointer's execute method with those timestamps as parameters. If it encounters a null space where no task is scheduled, it simply increments the timestamp and sleeps for the sake of the simulation. The code on the right is the task class keeping track of its progress as it runs to make sure it meets time constraints, and the simple task class executing a fairly trivial function. The code block on the left shows the main function, where we initialize our scheduler and our tasks. The 3 tasks are named workout, eat food, and take nap, representing important everyday activities. The function then adds the tasks to the scheduler, which then schedules and runs them for 1 cycle, which is equivalent to the 1 schedule frame or the time period of the least frequent task. The console output is shown on the right. First we compile the program. The next we run the scheduler. Now you'll notice that it's running in 1-second increments after it already added all the tasks and created the schedule. And the tasks are progressing as they go. And it'll run for 24 seconds because the entire schedule will use 24 time segments, and then we're representing those as seconds. All right, and now it finished. Thanks for watching. I hope you learned a little bit more about the scheduled task pattern, and here are some of the references I used to create this presentation.